multiplying radicals. And we did a little bit of this on Friday, but just to review real quickly. If you have -5 cube roots of 16, no, what would be good? Cube roots of 9 times 4 times the cube root of -6. That is something weird looking. Okay. Now, on Friday, of course, we were doing square roots, but it works for cube roots and on up. You just have to remember that even exponents, you have to be worried about positive on the inside and positive answers. With odd exponents, you could care less. So the first thing you want to do is reorder this, in your mind at least. Get the numbers next to the numbers and the radicals next to the radicals. Try to treat them as two separate individuals, because numbers underneath a radical do not behave as normal numbers. They have other things going on with them. So the first thing you're going to do, of course, is -4, Monday morning, -5 times 4, and then you're going to have the cube root of 9 times the cube root of -6. What property allows me to do this? Commutative and a little bit of associative. Okay. And then -5 times 4 is?
-20.
-20. And the cube root will stay around. So we have this cube root. Don't forget the little index of a 3. And 9 times -6 would be the next part, which would be?
-54.
-54. Now, you cannot leave that on a piece of paper because 54 is somewhat kind of big. So we want to see if we can break it down. So if I break it down, what's the smallest number that goes into 54? Don't worry about the negative.
1.
1's the most trivial number, but 2. Stick with prime numbers. 2 goes into 54 27 times, which is 3 and 9, which is 3 and 3. Again, you're going to see a lot of these numbers repeating themselves, so you get used to them. Now, this is a cube root, so what's coming out? A 3, because there's 3 3's. When the 3 comes out, it's going to run into this -20. But what else do I want to bring out besides the 3? I can bring that negative with a cube root. It doesn't matter if it's on the inside or if it's on the outside. I showed a simple proof before, but this is really the proof. If you have the cube root of -a cubed, that's the same thing as the cube root of -1 times a cubed. And then we can use our break apart property. The cube root of -1 times the cube root of, well, it doesn't even have to be a cubed, but you get the idea. That can kind of suck the -1 out front, and the cube root of -1 is? -1. So if there's a negative on the inside, you can also pull it out as a negative with cube roots, fifth roots, odd roots. All right, so I'm going to pull out this negative also. It's going to run into this negative out here and make it positive. And then we have the 3 times 20 making it 60. So we're going to get 60 cube roots of, what's left? The 2, this guy up here. So that would be your answer. So that's just a quick review from last time, and I want to just extend it into the distributive property and radicals. Just because they look different does not mean they behave differently. So if you have -2 square roots of 5 times 4 square roots of 10 minus 3 square roots of 15. The distributive property still kicks in. Now, when you're multiplying the first two together, for instance, the -2 square roots of 5, this whole thing is the number that's sitting out front. Don't separate it as -2 and square root of 5. It's one single number. When I take that huge chunk and I run into this huge chunk, it behaves just like over here. You're going to group the numbers with the numbers and the radicals with the radicals, but that's not distributive property, that's just commutative. You're just reorganizing things. So when I say -2 times 4, I'm just doing this first step over here, getting the numbers together with the commutative property. So -2 times 4 is? -8. And then square root of 5 times the square root of 10? square root of 50. If it's under a radical, it has to stay under a radical until you can group and pull it out.
But
All right.
If it's addition or subtraction, then you can't do the same. If they're not the same number, then you can't do it.
Okay, I'm confused. Where are you seeing?
Like the square root of 5 and square root of 10, if it's addition and subtraction.
Oh yeah, if it's addition and subtraction, you're stuck. But because they're multiplication, you can use that property. Square root of a times square root of b is square root of a.
Okay.
So multiplication and division are kind of nice with radicals. All right, and then you take the negative 2 square roots of 5 and multiply it by negative 3 square roots of 15. And again, you're going to use that commutative property. Get the numbers next to each other. This is, head work. Negative 2 times negative 3?
6.
Huh?
Positive 6.
I thought you said 7. Positive 6. Square root of 5 times square root of 15.
150? No, square root of 5 and 15 is 75.
75. What?
I was doing 10 and 15.
Ah. All right, so you get this nice little expression. Except for one problem, the numbers are way too big, and more than likely they're going to break up. So 50, what's the smallest number that goes into 50?
2.
2 and 25, which is 5 and 5. So I'm going to pull out that 5 because we're talking about a square root here, 2 factors. It's going to run into the negative 8 and make negative 40. Square roots of what's left behind? This 2 up here. All right, over here, 75. Smallest number that goes into 75. 3. 3 and 25. And 25 breaks up into 5 and 5. So again, I can group the 5s, pull it out. The 5's going to run into the 6. You're going to get a positive 30. And then you're going to get the square root of 3 is left behind. Can I do anything else from this point? No, you're stuck. Square root of 2 is like x, square root of 3 is like y. They have unlike terms. Don't force an issue. All right. What if we had something like, negative 2 square roots of 6 plus 3 times 5 square roots of... Try to come up with a decent one. 15 minus 2. What does it look like? Looks like a distributive property FOIL. Looks like 2 binomials multiplied together. They behave like polynomials for the most part. So with this one, you have to just keep focused on what you're doing. It's negative 2 square roots of 6 times 5 square roots of 15. That would be your first, or just distributing the first term to the first term. All right, and then negative 2 times 5? Negative 10. Square root of 6 times square root of 15? I don't know. 90? Square root of 90. And that would be your first. And then you're going to go and distribute this to the second one. So you have negative 2 times negative 2 is positive 4. This one doesn't have a square root. So the only thing I have to do is write down square root of 6. If you want to think of it, it's square root of 6 times square root of 1, which is square root of 6. All right, so that would give us first and outer. And then we have the 3 times everybody. So 3 times 5 square roots of 15. 15 square roots of 15. A little strange, but that's okay. And then positive 3 times negative 2, of course, is negative 6. So these radical expressions, if you get lost, just start treating them like polynomials, and things usually work out semi-decently. Should I leave the answer like this?
No.
No. What's the only one that simplifies?
15, right?
15. What multiplies to 15? 3 and 5. So that one's not going to break down. 6 is just 2 and 3, so he's not going to break down. But 90, I think he breaks down. Smallest number that goes into 90. 2. It's even.
45.
2 and 45. What's the smallest number that goes into 45? 3 and 3 and 9. 15. And 15, of course, is 3 and 5. So the only thing we can pull out here is a 3. The 3 is going to run into that negative 10 out front. So we get to our final answer. we're going to have 3 times negative 10 is negative 30. Square root of what's left behind? This 5, and also a factor of 2, that makes a 10. Then the rest of it doesn't change. 4 square roots of 6 plus 15 square roots of 15 minus 6. And this whole thing is the solution. This is the value of multiplying these two things together. Which one looks better? The beginning. But there's a reason for doing this. Alright, so one for you to do before I do the next part of this. Multiply that together. Ten seconds. You should be done. Did any of the radicals simplify? Okay, I hope so. Let's see here. 4 square roots of 2 times negative 2 square roots of 3 is negative 8 square roots of 6. 4 square roots of 2 times positive square roots of 6 is a positive 4 square roots of 12. Negative 5 times negative 2 square roots of 3 is a positive 10 square roots of 3. Negative 5 times positive square roots of 6 is negative 5 square roots of 6. Which one breaks down? At 12. You should be able to pull out a 2, and it leaves behind a 3. The 2 is going to run into the 4, so you're going to get negative 8 square roots of 6 plus 8 square roots of 3 plus 10 square roots of 3 minus 5 square roots of 6. Did anybody leave it this way? I hope not. There are like terms here. These both have square root of 3. So 8 plus 10 is 18. So we get negative 8 square roots of 6 plus 18 square roots of 3. Don't change that. Minus 5 square roots of 6. Oh, wait a minute. I didn't even see that. They both have square roots of 6. So negative 5 and negative 8. Negative 13 square roots of 6 plus 18 square roots of 3. I didn't plan on that. No, I didn't. I just made it up.
So you didn't give us enough time.
That's horrible. Alright, how about this one? Multiply those two together. Get an answer? What'd you get?
4 square root of
The cool thing about this one is the radicals all disappear. So, 2 square roots of 3 times 2 square roots of 3. You really have to go slow on ones like this. 2 times 2 is 4. Square root of 3 times the square root of 3 is square root of 9. But I highly suggest you do not write that down on your paper. When you get down to things like square root of 3 times square root of 3, just write the answer is 3. Don't even worry about the radical. Square root of 7 times square root of 7 is 7. Why? Because you're getting 2 factors of 7 and 2 factors of 3, so it's going to pop out right away. The mistake people make is writing the square root of 9, and then for some reason leaving it. Or even worse, writing square root of 6, which would really hurt things. So just put 3. So when you go 2 square roots of 3 times 2 square roots of 3, the 2's give you the 4. Square root of 3 times square root of 3 just gives you the 3. All right, 2 square roots of 3 times positive 4. It's positive 8 square roots of 3. Then inside, we get negative 4 times 2 is negative 8 square root of 3. And then negative 4 times positive 4 is negative 16. The nice thing here is these two cancel out. One's positive, the other one is negative. What property? Which one? Additive inverse. So 4 times 3 is 12, minus the 16, of course, is negative 4. So after multiplying all these radicals together and coming up with some atrocious looking expressions, this one actually turns out to be nice. Alright. Alright, so far we have a few rules of radicals. Let's just review them real quick. Rules. Number 1, we know the square root of a times the square root of b is equal to the square root of ab. Cube root also, 4th root, 5th root, but square roots are the most prevalent one. If index even, then a has to be bigger than 0, b has to be bigger than 0. If the index is odd, I could care less about a and b. But I'm going to write everything as square roots. Just realize that it could be a cube root or a 4th root or a 5th root. Rule number 2, cannot leave perfect root under a radical. Thus, all the simplification that we've been doing for the past couple days, taking out those common factors on the inside and pulling them out front, pairing them up, tripling them up, and so forth and so on. Rule number 3 pretty much works this way. Cannot divide by a radical. And going along with this, you cannot leave a fraction under a radical. Not leave a fraction, which is basically the same thing as rule number 3, is just kind of reiterating an idea. So for instance, rule number 3, this is a no-no. Do not leave anything that looks like 5 divided by the square root of 2. That's illegal. And I'll show you why in a second. And number 4, you cannot leave things that look like this. The square root of a fraction. Square root of a fraction. Now number 4 has its own rule, and it's basically the same as this rule up here. The square root of a times the square root of b is equal to the square root of ab. Since division is really close to multiplication, we can write it this way. The square root of a over the square root of b is the same thing as the square root of a divided by the square root of b. The square root of a over b is the same thing as the square root of a over the square root of b. And of course you can reverse that, and if you have a radical over a radical, you can combine it under one radical. But this one, for our purposes right now, is more important. So that would take the fraction and separate it out and have a whole number on the top or a whole number in the bottom. But then it falls under the, you can't divide by a square root because this one has a square root at the bottom now. So let me talk about that for a second and why those cannot have square roots in the bottom. When you take 5 and you divide it by 1.25, how do you do it?
Get rid of the decimal.
How do you get rid of the decimal?
Move it over.
Move it over. So if we were going to switch this over to long division, this would become, this would become 1.25 goes into 5. And you take this decimal and you move it over twice. That would make that 125. But if you divide or multiply this one by 100, you also have to multiply this one by 100 to balance it off. So you move the decimal place over twice, move it up top, and you go 0, 0. So then instead of 1.25 going into 5, it would be 125 going into 500. How many times does it go in?
4.
4. It goes in 4 times. So what if I had 5 divided by the square root of 3? What's the square root of 3 equal to? I don't know. I need your calculators here. What's the square root of 3 equal to? 5 divided by, give me the whole thing, 1 point.
1.732050808.
And of course, this goes on for ever. It's an irrational number. It's a decimal that goes on forever and never ever repeats. This possibly could be a 7, and the next digit would have been like 5 or 6. It had been rounded up, so we're not quite sure about that last digit. There's ways of finding out, but I'm not going to show you that. So if I need to divide 1.732050808 blah 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 into 5, how many times do I move the decimal place over?
A bunch.
What's a bunch? What's too many? Infinity. Impossible. So an infinite decimal motion. You can't do it. There is no way of moving the decimal over an infinite number of times because the decimal is never ever going to stop. So we cannot divide by a square root because technically it is impossible. And if you type it into your calculator, 5 divided by the square root of 3, all it gives you is an approximation, not a direct equals. So we have to have a way of moving this radical around, getting it away from the bottom. And the trick is this. If you have 5 over the square root of 3, I'm going to multiply by 1. Kind of like common denominator thing, but don't even think of it that way. I'm going to multiply by 1, the multiplicative identity. And I'm not going to change the value of this. I'm just going to move things around. I don't like square root of 3 in the bottom, so what should I multiply it by? Square root of 3. Because over here, remember, square root of 3 times the square root of 3 is just plain old 3. So I'll put a square root of 3 in the bottom, but if I put it in the bottom, I better put it in the top. So when I simplify this, it becomes 5 square roots of 3 over 3. And this is what's called a rational denominator, or rationalizing the denominator. With the advent of calculators, a lot of people don't think this is as important as it is, but it does come back to haunt upper-level math people. Because calculators can't save you when expressions are not numeric. And you still have to work with rationalizing denominators and sometimes rationalizing numerators. All right. So, this is really simplistic. My favorite example of all time is something like the square root of 15 over 3. Or even better, separate it, but what should you do? Yes. I love putting this on a test because I'll have someone split it into square root of 15 over square root of 3 and then multiply top and bottom by square root of 3, go through all that rigmarole, and the simplest idea is divide them. 15 divided by 3 is? 5, square root of 5. Anytime you can simplify a radical expression without going through a bunch of calculations. Do it. Simplify first usually works. Another way of writing this question is something like the square root of 40, I wrote it badly. Square root of 40 divided by the square root of 8. Keep them separate. And sometimes people see that radical in the bottom and they want to multiply top and bottom by the square root of 8, which shouldn't be written anyways, but we'll come back to that later. The first thing you should try to do is bring them together and see if it simplifies. So this becomes 40 over 8 underneath the radical. It's legal as long as you can simplify it. And 40 divided by 8 is? So you get the square root of 5. So don't jump into rationalizing the denominator. Use that as like a last resort, the last thing that you want to try. Of course, there are others that you just cannot get away from. 4 over 2 square roots of 3. I love this one too. What should you multiply top and bottom by? Why would you want to multiply by the 2? Oh, just because it's there. It's a danger. 2 is a rational number. You don't have to worry about him. The only thing you have to worry about is the square root part. So the only thing you should multiply by top and bottom is square root of 3. The 2 is rational. We don't care about him. Oh, I should have made this a 5. That way the 2 doesn't go away. So let's see here. Let me just write it over again. 5 over 2 square roots of 3. So you're going to multiply top and bottom by square root of 3. And the top becomes 5 times square root of 3, better known as 5 square roots of 3. What's the bottom become?
2 times.
2 times 3, better known as 6.
So if you came like 4, it would have been just 2 square roots of 3.
Well, if I left the 4 up here, the 4 and the 2 would cancel, and it would just be 2 over square root of 3. I didn't want it to do that, so I changed it. What gets worse? Oh, yeah, this gets worse. What if I had something like 2 over the cube root of 9? Now we have to be a little cautious. The cube root of 9 is an irrational number, and it cannot be in the denominator. So do I multiply top and bottom by the cube root of 9? I don't know. You tell me. What's the cube root of 9 times the cube root of 9?
Cube root of 81.
Cube root of 81. So let's see here. The cube root of 81. How do I break it down? What goes into it? Well, sure, 9, 9, which breaks up into 3, 3, and 3, 3. Of course, you're supposed to go with the smallest number. Well, I can take out a 3, but that leaves behind a 3. So that's not simplifying. It's leaving me a radical in the denominator. So it's not going to be a cube root of 9 and a cube root of 9 like the square roots were. Why did the square roots work? Well, because when you multiplied square root of 3 times another square root of 3, it gave you 2 factors of 3, so it popped out. What I need down here is 3 factors of something. Well, 9 is made up of 3 and 3. So if I split 9 up, I already have 2 factors of 3. How many more do I need? Just 1. So what I'm going to multiply top and bottom by is the cube root of 3. It's weird, but that's how it works. So now I have 3 factors of 3 in the denominator, and the cube root of 3 factors just pops out as a single 3. So on this side, we're going to get 3 in the bottom, and 2 square roots of 3, or I'm sorry, 2 cube roots of 3 in the top. And most people don't like that one. I don't know why, but the method is similar. And the reason behind it is, well, completely logical if you think about it.
What if there was another number? What?
Give me one. I can make up. You make up one.
Like 12.
12.
Or something.
Cube root of 12.
The cube root of 12.
That's all.
Can we go with an easier one before we tackle that one? That one actually
But
takes a
we
little
have that on the.
not cube root of 12. And the reason is this. If you had like 5 over the cube root of 12, 12 is made up of, let's see here. 2 times 2 times 3, right? So, you would need 3 factors of 2. So I need one more 2 over here. You would need 3 factors of 3, so I would need 2 3s over here. So I'd have to multiply top and bottom by the cube root of 2 times 3 times 3. Better known as 2 times 2 times 3. Oh, 2 times 3 times 3, I'm sorry. 18. So this would be 18. So the final answer here would be 5 cube roots of 18 over 6. Because you'd have 3 2s, so 1 2 would come out, and you'd have 3 3s, so a 3 would come out, and you'd end up with just a 6. That's why I would never ask that on the test. Too many pieces. I mean, the hardest I would probably go is something like 7 over the cube root of 2. How do I rationalize that? Well, the 3 tells you how many 2s you need. How many 2s do I have? Just 1, so I need 2 more. So what am I going to multiply top and bottom by?
4.
The cube root of 4. And then you get your final answer, which is not too bad. 7 cube roots of 4 divided by 2. It's not a hard technique, it's just you have to think a little bit more than the square roots. Square roots, you just go, plop in what's missing. This one, you have to plop in missing factors, and not just what is exactly there. But you don't see that often. Probably just in your homework, and maybe a silly question on the test. But the one that people usually make mistakes with is coming up. So let's go back to multiplying. I can't spell. And remember, what happens with an expression that looks like this? Alright, so multiply together step by step. What do I get?
9 cube roots of 4.
Yeah, I would say 9.
Oh, square roots of 4. Oh, with
2. 9 times 2. It's better just to say, well, square root of 2 times square root of 2 is just plain old 2, without the symbol on top of it, just plain old 2. And then here,
15.
plus 15,
Square root of 2.
square root of 2. Here,
Minus 15.
square root of 2. And then lastly,
Minus 25.
and what happens to the 2 middle terms?
Cancel.
They cancel. So what's left is 18 minus 25,
Negative 7.
negative 7. These things have a special name. So if we have something like a square root of b plus c and a square root of b minus c, these things have a name that's called conjugates. Conjugates. And what makes a conjugate is, number 1, it's a binomial, and number 2, it's off by 1 sign. Not 2, just 1. If I change both signs, it becomes a negative. But if I only change 1 sign, it becomes a conjugate. And conjugates always have this property that the 2 middle terms, the outer and the inner, will always cancel out. And what you're left with is a rational number. All right. So, for example, if I have something that looks like, 7 over 3 minus 2 square roots of 5, I can't leave that because it has a radical in the denominator. And this one's a little different because before I had like 2 square roots of 3 or 5 square roots of 2, and I said don't worry about the rational number, just worry about the radical. But if I just worry about the radical here, square root of 5, and I multiply top and bottom by the square root of 5, does that get rid of my radical in the denominator? No. It'll get rid of it in the second term, but it would introduce it to the 3, and you would still have a radical in the denominator. So what we're going to have to multiply by is its conjugate. So what is the conjugate of 3 minus 2 square roots of 5?
3 plus.
3 plus. Just change 1 sign, generally the middle one. So we're going to multiply the bottom by 3 plus 2 square roots of 5. And we're going to do the same thing to the top. Notice what I introduced in the bottom now. Nice little set of parentheses. If the top has two terms, you might want to also put that inside of parentheses, because this long bar is a grouping symbol. All right, so simplify. The top one you just distribute. 7 times 3? 21. 7 times 2 square roots of 5?
14 square roots of 5.
And that would be the numerator. Oops. And then the denominator. 3 times 3, positive 9. Outer is 6 square roots of 5, right? Inner is negative 6 square roots of 5. And you know you did it right because these two, if you add them together, are going to go poof, additive inverses. And then finally, this one. Negative 2 square roots of 5 times positive 2 square roots of 5.
Negative 4.
Negative 4 times 5. Just plain old 5. Because the square root of 5 times the square root of 5 is just 5. All right, the middle two cancel out. 4 times 5 is 20. So negative, negatives in the bottom lately. 9 minus 20? Negative 11. So you get 21 plus 14 square roots of 5 divided by negative 11. Now technically, you don't want to divide by negative numbers in a rational expression. So there's two places it can go. Number one, you can put it way out front here. The only problem with putting it way out front is sometimes it hides inside the fraction bar and you forget that it's negative. So the trick I always came up with is distribute it over the top. Because technically this is, negative 1/11 times 21 plus 14 square roots of 5. So I can take that negative 1 and just distribute it across the top. And that way the negative doesn't get lost. So I would write this as negative 21 minus 14 square roots of 5 divided by positive 11. And that way the bottom isn't negative. And you really don't want to leave negative numbers in the bottom. It's kind of like leaving negative exponents. But don't treat them the same. Now I just got to see how bad the book does this one. I don't think it does it really bad. Yeah, that's horrible. Of course, they do things really weird. The hardest I would go on a test. 2 square roots of 3 plus 5 divided by 4 square roots of 3 minus 2 square roots of 2. That'd probably be the hardest I'd go. Most difficult problem. And you don't treat it any different than that one over there. Nothing. Just do it exactly the same. Oh, and one of my favorite tricks is to make like this 4 here negative. Because what will happen is they see these two people will see these two negatives and make them both positive, and that's not a conjugate, that's an opposite. So the only thing you would have to change is one sign. And if you want, you can change the first sign. But most people decide to change the one in between, which is probably safer. So we're going to change the one in between. So the conjugate is just change the one sign. Put a lot of parentheses everywhere, because you're going to need them. And if you multiply the bottom by 4 square roots of 3 plus 2 square roots of 2, make sure you multiply the top by the exact same thing. I had a student in college algebra that would conjugate here and then conjugate again. So they'd end up back with the beginning. So make sure that this 4 square roots of 3 plus 2 square roots of 2 happens twice, top and bottom. And then it's just a matter of foiling it all out and trying to get the right answer. So let's see here. 2 square roots of 3 times 4 square roots of 3.
8 times
8
3.
Times a regular old 3. 2 square roots of 3 times 2 square roots of 2. It's going to be a positive 4 square roots of 6. There's no rush with these. Take your time. Make sure you're getting all the pieces correct. 5 times 4 square roots of 3. Try to get the word positive in there too. That way it gives you a sign. Positive 20 square roots of 3. And then a positive 5 times a positive 2 square roots of 2. Huh?
You said what?
Positive 5 times positive 2 square roots of 2. Positive 10 square roots of 2. All over, and then the bottom. Now, eventually what's going to happen is you guys are going to do shortcuts, and you're going to ignore the outer and the inner, and you're not going to see that they actually do cancel. I highly suggest you multiply it all out and make sure that the outer and inner products cancel. 4 square roots of 3 times 4 square roots of 3.
16 times 3.
16 times a regular old 3. 4 square roots of 3 times 2 square roots of 2.
6.
Positive 8 square roots of 6. Negative 2 square roots of 2 times positive square roots of 3, 4 square roots of 3. Negative 8 square roots of 6. We must have picked the right conjugate. They do cancel. And then finally, negative 2 square roots of 2 times positive 2 square roots of 2.
Negative 4 times 2.
Negative 4 times a regular old 2. Yay, finally a positive number in the bottom. So the middle two do cancel on the bottom. Don't force the issue on the top. They usually don't cancel on the top. Actually, I could say for sure that they don't, unless this is written really strangely. This is 48 minus 8. 40. So we have 8 times 3 is 24, plus 4 square roots of 6, 20 square roots of 3, and 10 square roots of 2. All divided by 40. If you leave this on your paper, I will take off a point. Why? Oh, because I'm mean. Yeah, well, other than that. Why would I take off a point? Just the 24 and 40?
Anything in the front?
Everything on the top has a common factor of 2, and the bottom also has a common factor of, it reduces. Everything reduces. So you can think of it as 24 over 40, 4 over 40, 20 over 40, and 10 over 40, if you want to separate it. But it's better just to say, well, what do they have all in common? And it's a common factor of 2. So divide everybody by 2. So this is 12 plus 2 square roots of 6 plus 10 square roots of 3 plus 5 square roots of 2 divided by 20. It's a mixture of the distributive property and simplifying. Everything has to be simplified by the same number. Now, if this last number was already 5 square roots of 2, you couldn't do a darn thing, because it wouldn't have a common factor anymore. But because they all are even, or all have factors of 3 or 5 or whatever, you can reduce, and it has to be all of them. And if you have to think about it mentally, what's going on is this. You can distribute that 40 to every single term. The problem by doing it this way is more than likely what will happen is you'll get things added together that don't have the same common denominator. That's the danger of it. So it's better just to pull out the greatest common factor at the top and see if it divides into the bottom. It's a little tricky if you're separated this way. All right. That's multiplying and dividing. What's next? Time? Not really. So let's try problem out of the book. Nothing hard. Number 42. The cube root of 125 a cubed b to the 4th divided by 64. What would you do? Just cube it and be done with it, yeah. That changes the answer, though. That changes the value.
Could you just make 25, 5, and 64?
No, when you do that, what are you doing? You're taking that cube root and breaking it into pieces. So split the top and the bottom, so this becomes the cube root of 125a cubed b to the 4th over the cube root of 64. I highly suggest you work with it as individual pieces rather than a huge group. Unless, of course, 125 and 64 had common factors that would, simplify. But it doesn't. All right, and then we can kind of separate this into two problems. We can do the top as a single problem, and we can do the bottom as a single problem, and just keep the answers top to bottom. So we can separate this. Cube root of 125 is 5. The cube root of a cubed is just a. The cube root of b to the 4th. Cube root of b to the 4th. How do you deal with variables?
B squared root of B.
3 goes into 4 one time, so that single factor of b goes out with a remainder of b behind. So we're going to get a b on the outside, cube root of b, over cube root of 64. That one you should know by now. It's 4. There's your answer. Don't have to rationalize. There's no radicals left in the bottom, but it does simplify a little bit. There's some other ugly ones. And those are just 4. Now let's do this one. Make sure we cover all our bases. Number 36. You would never see this one on a test. It takes way too long. Cube root of 4 minus the cube root of 6 times the cube root of 2. Well, maybe it doesn't take too long. Plus the cube root of 36. It just gets a little trickier because they all have cube roots. By the way, one thing. If you have the square root of 2 times the cube root of 5, can I multiply those two together? No. Different indexes, you cannot bring them together. It's only if they're exactly the same index. And the reason behind that is this is really 2 to the 1/2 power times 5 to the 1/3 power, and the bases are not exactly the same, so the exponent you can't mess around with.
Where does one of those
On the test. What
We
the-
wanted to do anything.
No, you just say you can't do it. But I've seen people go, oh, it's the square root of 6 times the square root of the 6th root of 10. Some weird like that. So when we do these, the indexes do have to be all the same. So cube root of 4 times the cube root of 2.
Cube root of 8.
Cube root of 8, we'll leave that for now. Cube root of 4 times the cube root of 36. What is it? 144. So it'd be positive the cube root of 144. All right, enter. Let's see, that'd be negative the cube root of 12. And then negative again, cube root of 216. 216. All right, should I leave it?
No.
Heck no. Sure. Cube root of 8.
2.
2. Cube root of 144. I was waiting for someone to say 12.
6.
That's the square root of 144. So let's see, 144 is 2 and
Half of 144.
half of 144, which is 72. Wow. Which is 2 and
36.
36. Which is 2 and
18.
18. I shouldn't have wrote this 2 over here. Which is 2 and, which is 3 and, good lord. Now this is a cube root, so all we're looking for is triplets. So here's a triplet. So I can pull out
2.
a 2, he's going to go out front. And left behind is going to be this.
3.
That's 18.
Oh.
All right, so the first one, bring it way down here. This is 2. This one, this is going to give us 2 cube roots of 18. So positive 2 cube roots of 18. Does this one simplify? 12? 12 is 2 times 2 times 3, so that's not going to go anywhere. So minus the cube root of 12. What about 216? That seems big enough. 2 goes into it. 108. 2 goes into it. 54. 2 goes into it. 3 goes into it. 3 goes into it. What can I pull out?
2, 3.
A 2 and a 3. What's left behind? Nothing. So the only thing that's going to pop out there is minus 6. And then 2 minus 6, of course, is negative 4 plus 2 cube roots of 18 minus the cube root of 12. That's what we're going to get out of it. Messy as all get go.